Hello today, Intro to Calculus number 3, optimization problems. We're going to do these as it says inside, kind of pre-calc style, and the deeper we get into calculus, we're going to find out how much easier calculus actually makes these problems to be solvable to us. However, it is important that we know how to do them in the pre-calc style because what we need to do is we need to build a function. Okay, our goal is to build a function that we can actually type into our calculator and maximize or minimize. Okay, what we're going to do is homework problem number 1 is going to be the first example in the lesson today, and then homework problem number 5, the Pepsi can, is going to be the second example for the day, and then you are left for the other, I believe it's 4 problems as homework. So an optimization problem here, number 1. You have 100 feet of fencing is used to enclose 3 sides of a rectangular pasture. The side of the barn closes off the 4th side. So make a sketch. Well, bottom line, we got a barn here, okay? And to no surprise, we have 100 feet. And we are going to make our pasture, except this one side butted up to the barn. Okay, that does not need to be fenced off. So this is going to be our pasture. And what we will be doing here in the end of this problem is we're going to maximize the area of our pasture for the cows to frolic in. Okay, so that was part A. We just had to make a sketch. Now, these might seem obvious to you. That's okay. But what they're doing is they're going to help others go through the thought process of how are they going to build the function. Okay, well, part B states, what does part B state, so I can read it appropriately here. What is the area of the pasture if the width is 5 feet? One side that is attached to the barn. The width is 5 feet, so we're going to be looking here. So here's our pasture. We have a 5-foot spot, a 5-foot spot. If we only have 100 feet of fencing, that means this third side is 90 feet. I'm going to put my little foot tick mark on there. And what would the area of that pasture be? The area would simply be my length times my width, or 5 times 90, which is going to give us 450 feet squared. Units are very important in calculus. Feet squared, feet, centimeters, you name it. Very important, okay? And then also, let's find the area if the width is 12 feet. Well, how does that change? Well, if I come across and I have 12 feet here, 12 feet here, well, I only have 100 feet of fencing, so that if I got 12 and 12, that only leaves 76 feet to close off that third side. Well, what would the area be? The area would obviously be length times width, or 12 times 76, which happens to be 912 feet squared. Okay, so obviously, as we change the width of the pasture, our area also changes. And what we want to do is we want to find the perfect width that is going to maximize our area in the end, okay? So part C, here is the function building spot, okay? So part C. If the width of the pasture is x feet, find an algebraic expression, A, in terms of x, for the area of the pasture. Well, there's my pasture again. If the width is x, okay, both widths are x, I only have 100 feet. That means my length here has to be 100 minus 2 times x, because I only have a total of 100 feet I can use. And if I subtract x feet and x feet, that is what's left on that width. So my area function in terms of x would be what? Well, length times width, or width times length. So it's going to be x times 100 minus 2x. Why do we need this in terms of one variable? Well, the reason we need this in terms of one variable is right now, so we can type it into our calculator, number one, and use the graph to find a maximization or a minimization of the problem. And also, we're going to find out later on in calculus, we need to write these in terms of one variable as well. So when we do our mathematical calculations on it, we are able to do it in terms of one variable for a very specific reason that will come about later on. So you could also think of your area function as 100x minus 2x squared as well, okay? And I'm sure you remember this. However, y, okay, my y variable, that's my area, and that is also in terms of my a of x. That's just another abbreviation for y. And x in this problem is width of pasture. Okay, really important to know what we are looking at. Okay, so on your calculator, we're going to draw a complete graph of a of x. Well, so what I'm going to do is I'm going to pull up my calculator here in a second, and this is going to be D, and I'm going to make a sketch of what my calculator looks like. Okay, so let me grab my calculator, and I already had it typed in here, and the reason I typed it in this way was I wanted to make sure everybody knew that if you have a variable, or remember, a variable outside of a parenthesis, you have to unconditionally put the multiplication sign there. Otherwise, your calculator gives you an inaccurate dimension or some error message and it will not graph, okay? So what we're going to do is we are going to graph that. Oh boy, can't really see it. Well, this is really a pretty easy one, but remember, okay, how would you adjust your windows to see what we need to see? Well, pretty obvious. If I think of the graph of this thing is going to be a parabola, and if I think about, you know, what I know about a parabola, it's going to be a concave down. And what are the x-intercepts of my parabola that I'm looking here? Well, because right here I'm factored, I can see I'm going to have an x-intercept at 0, and I can see here I'm going to have another x-intercept out here at 50. And somehow, some way, this graph is just going to go woo like that. And that is what we're going to be looking at, because I can't have a width bigger than 50 because I don't have enough fencing to do so. So that's important to know. So as we are changing our windows in here, and also as I'm changing my windows, check out what happened to my y value or my area. Here, my area went from 450 to 912. I don't know. What do you think? It's going to go up or down. Think of what you know of a parabola here. Okay, you know it's going to have an axis of symmetry somewhere in the middle. Should be around where x is 25. Just thinking back. Okay, so what we want to do is we want to make sure we're going to change our menu, our window, and our window settings. And I'm a kind of guy, I like to see my x and y axis as much as I can. So I'm going to go from -5, and I'm going to go out to about 55. And I'm going to put my x scale, I don't know, I think I'm going to put my x scale, what the heck did I put my x scale at? I think I put it at 5, we'll see. And my y minimum, because I know I'm getting really big, I'm going to go from about -100 to, I don't know, 1,500, 2,000. I'm going to go big or go home. And because my y scale is so large, I'm going to divide that up by about 100, and I'm going to hit enter. And I'm going to hit my graph, and lo and behold, look at that little devil. There it is. I can move that over. So bottom line, that is the graph that I was looking at. So how I would ask you to communicate that in homework is just come down here, and underneath it, probably say something like, yeah, my X windows, I'm going to go from -5 to 55. And my Y windows, I'm going to go from about negative 100 to 1500. And we don't all have to have the same windows. As long as we can see the same graph, our shape will be the same, but it might look a little bit, different to us. So, and E. So we're on to part E here now. And part E says, what values of X make sense in the problem situation and why? Well, obviously, my widths have to be between 0 and 50. They have to be between 0 and 50. Because if they're to the left of 0, just remember what your graph is actually doing in your calculator. It's not graphing one spot, it's making the whole thing. Then you would have a negative area, not good. And if we had a width of 0, we could not include 0. That's why I put a parenthesis there. We couldn't include 0 because then you don't have a pasture, and your width can't be 50 because then you also don't have an enclosed pasture. So go between 0 and 50. The other way you could say it is X has to be greater than 0 but less than 50. Those are the only values that make sense here. So F, we're going to use our graph to determine the dimensions of the pasture if the area is 500 square feet. Okay, so here we go. Here I'm going to show you two different ways to use your graph. On the graph, we're going to, if we're using just the graph, okay, where the heck is 500 square feet over there? Well, in order to see that, if you remember, what we can do is we can hit tab and we can graph the horizontal line of 500. And then we can see the intersection of these two, and that's where it would be. How did we find our intersection? Well, we went Menu, Analyze Graph, Intersection, and we went to the left of the intersection, to the right of the intersection, and we did another Analyze Graph, Intersection, and we found these two intersection points right here, okay? So that's one way to do it. So what we just found here, okay, using our graph, we had the graph, we graphed our area that we were looking for over how our area changes with respect to the width, and there are actually two of them, shockingly, because it's a parabola. Let's get out of there a second. So now I'm just going to come down here, and we're going to say, well, what were those values? Well, I could see on my graph, I could see it's when X was approximately equal to, I'm going to use the approximate, because remember, we're rounding to 3 decimal places. We were at 5.635 feet. And when X was approximately equal to, the other one was 44 point, ooh, that's a crappy 4. I better fix that one. X was also approximately, I'm going to say or, 44.365 feet. Now, remember, this problem isn't asking what is X equaling. They're saying, what the heck are the dimensions if the area is 500 square feet? These are not dimensions. Those are just one of them. So I know my pasture is going to be 5.635 feet by, well, I'm getting all nutty up there with that. I'm just going to use my tick mark for feet. Feet by, how many feet are these? Well, easy enough to grab your calculator, and we can add a page to that calculator and add a calculator page and say, well, I know 100 minus 2 times, what was that? That was 5.635 feet. Oh, it must be 88.73 feet. And the other one would be 100 minus 2 times, what was my other one? 44.365 feet. So the other one was 11.27. So I know the dimensions at 500 feet are going to be 5.635 by 88.730 feet, or another dimension could be 44.365 feet by 11.27 feet. Now there is another way to do these. You don't have to have your graph, okay? We use this, actually I use this a lot in calculus, okay? This is why you have the CAS model. We are going to use the solver, okay? And what we are going to do is we're going to hit Menu, Algebra, and we're going to hit number 1, Solve. And what do we want to solve? We want to solve our equation. When is the area 500 feet? When is that equal to what my function was? And I can type in either version of the function I have, but I'm just going to say 100x, what was it, minus 2x squared, okay? And then what we need to do is we need to hit a comma and tell it what variable we want to solve it for x, okay? And watch the magic going on here. We don't have to graph it and do the graph. We just hit enter. Bada bing. Oh, I'm in exact value mode. So now I need to go up and I'm going to re-grab that thing. And then I'm going to hit Control, approximate. Then it'll give me my decimals. And you can see it's quickly spitting out my 5.635 or my 44.365, and I can get those right out of the solver and I don't even need the graph. Okay, we do use solver a lot in this class, and it is pretty stinking handy. So that was a quick rundown. If you need to back up and look at that solver again, you can. Part G says use your graph to determine the dimensions of the pasture if the area is to be as large as possible. Well, I'm pretty sure everybody knows what that means. And that is saying whoa, need something to write with that is part G. What the? I don't like the fat writing. Go there, I'm going to go there. That is part G. That's basically saying, hey, take your graph. We know we're here at 0. We know we're here at 50. And we know it's a concave down parabola. Because it's a parabola, we know it has an axis of symmetry, which is regardless, we're looking for that point right there, right? So, good thing we've just been practicing that a little bit last week on our calculators. So all we need to do is come back and grab our calculator, go back to our graph page, and we want to ask the calculator, could you please analyze that graph and give me that maximum? And I want the maximum of the blue graph, so then I'll go to the left, I'll go to the right, and they're giving me my maximum, okay? Don't fall into the trap. Do not fall into the trap. The maximum is 1,250 square feet. The dimension of the width is 25, okay? So when we're looking here, we know, hopefully, this is 25, comma, 1250. I think it was 1250. Was it 1250? It was 1250. And there we go. Get rid of that. Come up there now. Get them off of there. So I know my width. Okay, now again, they're asking for a dimension. I know the width is 25 feet. Well, what the heck is the length? Well, pretty simple. Find the length. It's 100 minus 2 times 25. Pretty simple to see it's 50 feet. So my dimensions are 25 feet by 50 feet. That maximizes the area of the pen. That gives the cows the most fun, the biggest fun zone to frolic in. Okay, and that is the first problem. The second problem we are going to go to is we're going to go to problem number 5, the Pepsi can. The reason I'm going to go to problem number 5, the Pepsi can, is because this has a lot of formulas. One thing you do not have to memorize in calculus, you do not have to memorize geometric formulas. You don't have to know the volume of a sphere is 4/3 pi r cubed. You don't have to know that. Any geometric formula on the AP test or my test will be given to you because they're going to give it to you. Okay? So they have a Pepsi can is constructed to hold 355 milliliters of liquid. Note on the side there, 355 milliliters is equal to 355 cubic centimeters, which is 12 fluid ounces. Okay? Now we're going to sketch a picture, blah, blah, blah. We're going to go through this whole thing. The whole point of the problem is to find the dimensions of this particular can that will minimize surface area, yet still hold exactly 355 milliliters of Pepsi or fluid. Okay? So first thing we're going to do, well, not everybody. Kruger is a very visual person, so I'm going to start with A. I'm going to sketch a picture of my Pepsi can and bring it down, and that's going to come down. And the back side there I usually can't see, and it's hidden. That sweet little Pepsi can on the bottom has a radius. That sweet little Pepsi can has the exact same radius on the top, and it has a height right there. Isn't that a nice sketch? From here, if the radius of the can is 2 centimeters, okay? If the radius of the can is 2 centimeters, what is the height of the can? Well, I guess we need to know and remember how to find the volume. If you remember how to find the volume, volume equals pi r squared h. That's how you find volume. Well, if I know the radius is 2 centimeters, how tall is it? Well, I already know it's holding 355 milliliters, which means I have pi times 2 squared times h. Well, that would mean h is equal to 355 divided by 4 pi. I encourage you to type these in to make sure, to make sure that you're getting the appropriate answers, because when we round this, that means h is approximately equal to, if the radius is 2 centimeters, that means its height is 28.250 centimeters tall. If r equals 2 centimeters. Okay? And then they also want something else here. They also want to know what is the surface area of the can. Oh, well, because that's what we want to minimize. Think about it. If you own Pepsi company, you're not learning this. You're paying people how to do this. But if you minimize surface area, you are going to hopefully start to maximize your profit because you're using the least amount of material to make it. So, surface area. How do we find surface area? Well, surface area is going to be top of the can plus bottom of the can plus the lateral area or the side of the can, which when you cut it out, it just lays out into a rectangle, okay? So you know how to find the area of a circle. That's pi r squared. There's another pi r squared plus, if you take that cylinder, cut the top and bottom off and slice it up, well, the length is going to be the circumference of that circle, right? So that's going to be 2 pi r, and then there's my height. So plus 2 pi r h. So that's how we get the surface area of a can is actually, excuse me, 2 pi r squared, because it's two bases, plus the lateral area. And there we got it. Okay, well, they want to know what is the surface area. Well, what the heck is the surface area? Well, I do know 2 times pi times, I know the radius is 2 squared plus 2 times pi times 2, there's the radius, times this h right here. We just calculated it, the centimeters 2. We know this is 28.250. That means the surface area is approximately equal to 380.133 centimeters. And because it's surface area, it's centimeters squared. If the radius is 2 centimeters, it can give me, that's how I will get the surface area. Okay, well, now it's asking me again. We're going to go through this whole thing again here now, and we're going to say part C. And I'm going to chop this off. And the part C says, if the radius of the can is 6 centimeters, what's the height of the can? There's a reason why we're doing this twice, okay? So we know the volume equals 2 pi r volume is pi r squared h. Okay, we know the volume is 355. Our can volume is never changing in this problem. It's always going to hold that much. Equals pi times 6 squared times h. So h actually equals 355 divided by 36 pi, which means h is approximately equal to how many centimeters? Well, it's a short little fella now. 3.139 centimeters if r equals 6. Okay. Well, now that we know the height and the radius, well, now we can find the surface area. Because again, surface area equals 2 pi r squared plus 2 pi r h. Well, that means my surface area is going to be 2 times pi times 6 squared, because my radius is 6, plus 2 pi times 6 times, if the radius is 6, my height is 3.139, which means my surface area is approximately equal to 344.532 centimeters squared. Okay? Obviously, you can see as the radius changes, the height changes, which changes the surface area of the can. No big shocker. Okay? But we want to minimize the amount of material that we are going to use to hold these 12 fluid ounces or 355 milliliters. In order to do that, if you look at the surface area, okay, there's more than one variable in there. We can't type that into our calculator. It won't graph anything for us, okay? So what we're going to do is we're going to go on to part D. And part D says, if the radius of the can is x centimeters, what is the height of the can in terms of x? Well, we know volume, because we knew the volume, is, what is our volume? Pi r squared h. Well, we know the volume is 355. Again, that never changed. What's changing is our radius and height to hold 355 milliliters. Pi, well, radius is x squared times h. Oh, what is the height? The height actually equals 355 divided by pi x squared. So check it out. We just wrote a function. We just wrote the height in terms of x is 355 over pi x squared. Well, now the height is in terms of x, okay? So because I know, I'm just going to get rid of this. I don't really need this here. So I know my height is 355 divided by pi x squared when the radius equals x. Kind of important there, because now I can come to my surface area equaling 2 pi x squared plus 2 pi x times h, and I can plug. I'm getting a little ahead of myself because I want that to still be my radius. I don't want to confuse anybody. Sorry. Radius squared and radius. I know my radius is x, and I know my height in terms of x, so when I substitute those in there, 2 pi x squared plus 2 pi times x times, that h is an ugly little monger, it's 355 over pi x squared. Now I have an ugly function only in terms of x, so I will be able to graph it. And all I'm going to do before I graph it is I'm going to clean it up a little bit. I'm going to say my surface area in terms of only x now equals 2 pi x squared plus what? Well, check it out. Fraction fun. With this multiplication, that pi will cancel that pi. That x is going to cancel one of those x's. And I know 2 times 355 is what? 710 all over x. And I can write, now I've written my surface area as a function of x, where x, once I know my radius, my function automatically converts my radius and puts the height and does everything in terms of it, okay? So this is what we need. We need one variable to get it into our calculator, okay? If you really wanted to, you could simplify this, and you could also call it, in terms of x, you're going to have 2 pi x cubed plus 710 over a common denominator of x. Either one is fine to type into the calculator. It doesn't matter which one you do, okay? So now we found the surface area in terms of x. Now we want to find the dimensions of the can, both height and radius, that will minimize surface area. Well, I'm just going to come up here because we're going to enter this and we're going to get a weird window, okay? So we also want to go through what we did up here, okay? Notice we have some pretty big surface areas. Our radius really didn't get too big. When we put our radius to 6, it was a really short, fat can, okay? So it'd be kind of hard to drink out of that little guy. But so what we're going to do is we are going to grab, or I'm going to grab my graphing calculator, and I'm going to start a whole new one. I'm going to do a whole new document. I do not want to save it. I want to graph. And I am personally going to graph to, remember where your pi is down here in the bottom, and then you pick your pi, and then I'm going to have an x squared plus, then I'm going to put 710 over x, so I'm going to do my fun control divide, and I'm going to say 710 over x, and then I'm going to hit enter, and there is my graph. Looks kind of weird, doesn't it? So what does that really mean? Well, I think that means tab, come up, it threw it in there, okay? This should be an upward opening parabola, correct? That all makes sense to us there. And what we are going to do is we're going to go into our menu and we're going to change our windows here. And my window settings, well, I'm still going to say -5 for my minimum. My maximum, I'm not thinking is going to be much bigger than 10. My auto, this scale, I can go by ones, I'm thinking. And my minimum, I like to see my x-axis, so I'm going to say -50. And my maximum, I'm going to throw it up to about 500 once. And I'm going to go by 50s. And hopefully, whoa, check it out. And we can kind of see a parabolic looking little critter there. So where would my minimum be? If these are by 1, 2, 3, 4, 5, 6, I can see there's when 6 was. Here's what it was when 2 was in there. Okay, we want to minimize this. So we would obviously, hopefully it's obvious, and don't get wigged out by this bottom piece down here, okay? Because it's over x, it's a rational function. There's a vertical asymptote at 0, so I can never really hit 0. It's always going to go up and go down on the other side. Okay, but it's going to have that little parabolic shape because I need a minimizing spot on it. We're going to say menu, analyze. This time we want the minimum. Boom, boom. There it is. So check it out. This is my surface area graph, okay? So if my radius is 3.837, I am minimizing my surface area at 277.545, but they want to know what are the dimensions of the can that will minimize surface area. So this little bugger, come on baby, drop that off, bring this down, extend it up yet for my part E. We just pulled off the graph that the radius is 3.837 centimeters. You minimize surface area to, I forget what it was, 277? 277.545. Okay, you don't have to write this here. That irritates me when I do that all the time. You'll all laugh at me when we come to school, and I always do that. 277.545. Whoa. 277.545 centimeters squared. Okay. But they want to know the dimensions to give the dimensions of my original can. Remember, we not only needed radius, we also needed height. We know the radius is 3.837 centimeters. What the heck is the height? Oh, we need to fall back to volume equals pi r squared h again. Because we know the volume's 355. We know pi. We know the radius is 3.837. Got to square that to get h. So h is approximately equal to, and I'm just going to do the math now. Well, I'll put 355 divided by pi 3.837 squared. And I'm going to get technical here. I'm not going to say it's approximately equal. I'm going to say it's equal to. And then I'm going to say now h is approximately equal to, and I'm going to type that into my calculator. And I'm going to say the height comes out to be 7.675 centimeters high. So my dimensions, radius and height equals 7.675 centimeters. And that's how we maximize and minimize. The kicker is, in order to do it, we need to be able to build a function in terms of only x so that we can type that little bugger into our calculator, modify our windows, so we're looking at the appropriate graph that we can see when does it minimize, when does it maximize, and then use our other formulas to actually find the dimensions, okay? So your homework is to do the rest of these problems. There are, I think there's 4 of them. You need to do 2, 3, 4, and 6. Other than that, have a great day.